Welcome to EDU World Space.
So I'm going to solve problems 105 and 106 together because they look at the same structure. We have a cables here supporting a platform. So we have one cable connected to ground, goes to point from A to B, and then another cable from B to C, and then from C back to ground at point B. We know point B is 2 feet from the origin in the horizontal direction and some unknown distance below the origin in the y direction. Point C here is 5 feet in the horizontal direction and 3 feet down. And point D is just 8 feet in the horizontal direction. So we have this platform and it's connected through cables here to points B and C. We can figure out, if we look at a free body diagram of just this platform and have equal and opposite forces on it, we can see that FB, in terms of the weight W that is hanging from this platform, has a y component of minus W 3 minus x over 3. And we can see that when x equals 0, this is minus W, and when x equals 3, it's 0. So when it's over here, it's fully supported here. When it's over here, none of it is supported by this. And likewise over here, we have minus Wx over 3. So when x is 0, this is 0, and when x is 3, the weight is fully supported over on this at this point. So in this problem, we have let's see here, we have 6 unknowns. We have the 2 components in each of these support points. So there's 4. We don't know what YB is, this distance here, and we don't know what the tension in this cable is, but we do know the direction, or at least in terms of YB. So we have 2, 4, 5, 6 unknowns. So we need 6 equations to find those. And we'll get one of those equations by just cutting through these ropes attached to the platform and exposing the forces connecting the ropes to ground. And some of the forces, the force balance, gives us this equation. And then if we take moments about point A, we get this moment equation for the moments. That has to be 0. And then we can take a cut. We can cut through here, and look at this substructure that I'm circling. And in that case, we have FB plus FA plus FBC exposed. And then moments about point C, we can get that FB creates a moment, and we can get our CB knowing these 2 things. And then FA creates a moment about point C, and our CA is just negative of our AC. We also know this unit vector in terms of, because we know these 2 things, and we can get this in terms of YB. So that just becomes a function of Y, so Y sub B there. So in the first problem, or in problem 105, we are told that x here is 2 feet, and that this is 300 pounds, and we want to figure out which cable has the segment has the greatest tension, and also figure out what YB is. So we have 6 equations, and we have these 6 unknowns. We can figure out the tension in this cable knowing these 2 things, and the tension in this cable knowing these, and then we can figure out the tension in this cable just that as one of our unknowns. So we find FAX, FAY, FDX, FDY, FBC, and YB are our unknowns, and we have 6 equations to solve for those. What I did here is I solved everything in terms of x, and I plotted all of the tension in each of these spans as a function of x, going from 0 to 3. Now we have FBC actually has a minimum here somewhere. I didn't calculate where that is, and then it comes up here. But we can see that it's less. It's always in all of these cases. So this segment here has the least tension in it, no matter where x is. Turns out at x equals 2, these two are, as is the point where these two cross. Not sure exactly why that is. Probably has something to do with the spans being 2 and 3 feet apart, and then the platform being so that the x being 2/3 of the way across the platform. I'm not sure, but that they actually turn out to be equal right here at x equals 2. When x is less than 2, FA is bigger than FCD, and when x is greater than 2, FCD is greater than FAB. But at x equals 2, we get FBC is 158 pounds. FAB and FCD are both 212 pounds. And we can also find, when we put x equals 2, I didn't plot it, we could actually plot YB as a function of x, but I didn't do that. But if we plug in x equals 2 and solve, we'll get that YB is also 2 feet. Now, if we set in the problem 106, we have, we're given YB, and given YB, we can then basically we have one less unknown here, okay? But we have one more unknown, as we don't know what x is. So if YB is given, then actually x, we can find x, and there's no sense in you think you might have to maximize it, but actually it's known once you know YB. So the idea here is then from our 6 equations, we'll get these two: this force, this magnitude of this force, and we'll know this because we know YB, and we'll also get x out of this equation because we know the relationship here. So it turns out that we go through and crank through that algebra, we get that x equals 18/7 feet. I didn't calculate that out numerically, but again, I'm plugging in a calculator. 2.2147, a little more than 2.5. Right. So, and then we can also figure out that if we just leave W as a variable, we'll find that each of these, the tension in each of these segments just scales linearly with W. And to figure out which one is the maximum, we just need to figure out which coefficient is the maximum, and that turns out to be in FCD. And shouldn't be surprised because the weight is over here. So a lot of the load is being carried in this segment. So that gives us the maximum, and if we want that to be no greater than 200 pounds, then the weight can be no greater than 247 pounds.